All right, let's get into this review here. So for section 1, we learned about a couple of factors that affect gases. First one is pressure, which is a measure of the number of collisions that gas particles have on a surface. There are 4 or even 5 different ways we can measure pressure. So our first one here is we can measure it with kilopascals. We've got 1 atmosphere, 14.7 psi, or 760 millimeters of mercury, which is the same as 760 torr, or even 760 bar. Now another factor is temperature, which is a measure of the speed of kinetic energy. So temperature measures how fast particles are moving. And we don't like Celsius because it has negative, and same with Fahrenheit. Both the scales have negative, so we need to work in degrees Kelvin. So there's our magic number, 273.15 kelvins equals 0 degrees Celsius. So how do we use this in a problem? Well, the hottest temperature ever recorded on Earth was 56.7 degrees Celsius. Let's convert to Kelvin. So all we need to do is take our magic number, 273.15, and add it to the temperature in Celsius given in the question, and double check my math, but 329.85 kelvins should be our answer. Well, what happens if this is negative? Well, the coldest temperature ever on Earth is minus 89.2, and how will we convert this? We'll do the same thing. We're going to take our magic 273.15, and this time add it to our negative 89, so obviously it's going to go down. And again, double check my math. So this one's now 183.85. So with kelvins, you can never have an answer lower than 0 because that is absolute 0. Now, wrapping up this section where there's a few conditions to know. STP, standard temperature and pressure. Those would be our 273.15, 101.3 kilopascals. And we also have standard ambient temperature and pressure, which pushes our temp a little bit higher and our pressure a little bit lower. Moving on to section 2. We're going to be looking at 3 ideal gas relationships in this section. So pressure, this is standing for pressure right here. Volume, that's going to be our big red balloon. And temperature, there's our thermometer, are all factors that can affect the size and behavior of gases. Now there's one other thing to consider, and that's the amount of gas we have present in each situation. So the amount or moles will be constant throughout the lesson, and so we're not going to consider it. So we'll disregard the moles for now. So 3 ideal gas relationships can be determined by holding one of these 3 factors constant and seeing how the other 2 affect each other. These are going to be the outcomes that we're going to go ahead and prove in this lesson. So let's firstly, in no particular order, let's look at pressure versus volume while keeping a constant temperature. Now before we actually get into the math and equations, it's probably a thought experiment is a good idea. So let's think about a red balloon. What would happen to this balloon if it were allowed to float up high into the atmosphere? So as you go up in the atmosphere, there's less air molecules, so there's actually less pressure. So what happens to the volume of our balloon if there's less pressure on the outside of the balloon? Well, it's going to start to get bigger. There's less pressure, and bigger, and bigger, and bigger, until bang, it explodes. So if we consider this, we're actually going to be able to derive our first gas law. So as pressure decreases, the volume of the gas increases. Again, note the keywords. As pressure decreases, volume increases, and vice versa. Let's just look at one of these scenarios here. So what this means is that volume is inversely proportional to the pressure. So the volume is it's doubling as we half the pressure. The volume is tripling if we 1/3 the pressure. They are inversely proportional. One goes up, one goes down. Now we can represent this mathematically. So our volume is inversely proportional to 1/P. Now we also have that constant, the constant temperature to think about. So we're going to stick a little K there. So that K stands for the temperature. All right, that. Now let's simplify this a little bit. So we're going to say V1, instead of the Jesus fish there, we'll just say equals. And I'm just going to put that K up top. Now I've put ones here because there's always sort of a before and an after situation. So this is kind of like the before situation. Now at the same time, there's also an after situation. So we'll call this V2. So V1 could be our balloons on the ground, and V2 is our volume as it's floating up into the sky. And we have the exact same thing going on here. So we have V2s and P2s. Let's simplify this a little bit in the next step. So we're going to cross multiply that P over to the left-hand side. So P1 V1 equals K. And do the same on the other side. P2 V2 equals K. This K and this K are exactly the same. So if both of these expressions are equal to K, then we can simplify this by simply setting P1 V1 equal to P2 V2. And we've arrived at our first gas law. We're going to call this Boyle's law. P1 V1, P2 V2. So all that derivation we just did has ended in this. So let's go ahead and try out this equation in an example problem. A 4.2 liter red balloon. Now I recommend you, when you go through these things, you underline the numbers and the terms that go with it, or the units, because the units are going to tell you if it's a pressure, a volume, or a temperature, or something like that. All right, so we want to determine the new volume. So we've got kind of our before situation with this stuff right here. Now let's identify this here. This in liters, that must be a volume, and since the first one we came across, we'll call it V1, and kilopascals is a pressure, so this is going to be our P1. So let's go ahead and fill those into, and it goes on to say determine the new volume, so that'll be what we're going to calculate, and we have it decreased to 70 kilopascals. There we go. Now, before we even proceed, I want to point out that our pressure terms can be in millimeters of mercury, torr bar, kilopascals, there's a few of them. Anyway, so they need to be the same though. So we are working, both values are in kilopascals, so that's fine, we can proceed. If one of these was not in kilopascals, you need to do a conversion that you learned about in Unit 1, make sure they're both in the same, and then you can proceed. So once you have your three variables figured out, I want you to write the equation, plug in the unknowns. Now at this point, we're going to do a little bit of rearranging. It's probably easiest just to divide both sides by 70. That says 70, and that says 70 as well. And so in essence, V2 is going to be equal to 100 times 4.2 divided by 70. And if you grab your calculator and try that out, you get 6. Now, what are the units on this 6? Well, it's a volume. If you go back over here, you'll notice that this 4.2 is in liters. So if this is in liters, then our answer here is also in liters. Boyle's law, PV, Boyle's law. Let's look at the second one. Randomly here, we're now doing temperature versus volume at a constant pressure. So I want you to think about that big red balloon and a refrigerator. And what we're going to do with that balloon is we're going to shove it in. So what would happen to the balloon if it were placed inside of the refrigerator? So think about that. You put the balloon in, it gets really cold. The molecules inside the balloon start to move slower. They slow down. And as they slow down, the volume of the balloon is going to shrink. So there we go. It shrunk and then it exploded because it got so small. So we have come up with our relationship here. So as the temperature decreases, the volume of the gas decreases as well, and vice versa. So they're either both going up together or both going down together. So that's different from our first gas law. But what we can say is that these are in proportion. They're either going up or down together. So let's do our derivation. Now, so this time we're going to have V is in proportion to T, but we can't forget about that constant. And so let's mathematicalize this. So V1 is now equal to T1 times K, and V2 equals T2 times K. Let's put this all together. Now this one divides out now. So we're dividing both sides by the T. And again, we have these K's, so we can finally put our gas law together. Bam, we have our second gas law known as Charles' law. Charles's law. So VT1, so we've got volumes and temperatures here. So let's apply this gas law now in an example. All right, so a 4.8 liter red balloon, so that's going to be a volume, liters is volume, is filled at 25 degrees Celsius. Celsius is a temperature. So we've got a V1 and a T1 here. Let's make sure we keep these together. And let's determine the new volume of the balloon as we're decreasing to 10 degrees Celsius. So there's our T2. So we have our numbers. So our V1, T1, let's start filling them in. 4.8, 25, unknown, and 10. We'll write our gas law, plug in our values. If I'm going too quickly, you can always pause the video. Now we're going to do some cross multiplying, and in the end, V2 is going to be equal to 4.8. So the way I would cross multiply this is 4.8 times 10, and then you end up dividing by the other one, divide by 25, and we get an answer, if you grab your calculator and try it out, of 19.2 liters. Now let's think about this answer here, 19.2 liters. We said that both of these variables are either going up or down together. So we start with a volume of 4.8 and a temperature here. Our temperature went down. So did our volume go down? It did not go down. This answer is wrong. We have done something terribly wrong, and I hope you noticed what it is. Very few kids make the observation correctly right away. Do we work in degrees Celsius? What was one of the very first things I taught you in section 1? That's convert to kelvins. We need to redo this problem. So 4.8, now there we go. So remember, to convert to kelvins, we're simply going to add the 273.15. So we get 298, and our T2 is actually 283. So when we write our gas law and plug everything in, that's what it's going to end up looking like. And if our temperature went down, our volume should go down a little bit. If you do the calculation, 4.56 is lower than 4.8. So that is our correct answer. So there's your lesson on always work in kelvins. Let's go on to our third gas law. Third gas law, temperature versus pressure at a constant volume. And how do you have a constant volume? You definitely can't use the balloon anymore. So what would happen to the pressure inside of a thermos if the temperature was to decrease? So there's our thermos. That's got a fixed volume, a constant volume. What happens if we jam that out in the snow or put it in a refrigerator? What would happen to the molecules inside? Well, those molecules inside would start to move slower. We know that pressure is measuring the number of times collisions occur on a surface. So if those particles are moving slower, they're going to have fewer collisions, meaning the pressure is going to decrease. So as we've decreased our temperature, the pressure is also decreasing. Bang. So as temperature decreases, the pressure exerted by the gas decreases, and vice versa. So pressure is in proportion to temperature. So this should be the exact same as our previous gas law. So we're not going to need to go ahead and derive this, because all we've done is we've swapped out volume for pressure. So there, in fact, is our third gas law. This one is called Gay-Lussac's law, named after Joseph Gay-Lussac. So pressure and temperature. So let's give this one a go. There's a nice little wrinkle I can throw into this next and final example problem here. So a thermos is at STP. Determine the pressure of the system that the pressure will exert at 150 degrees Celsius. So noted, it's not converted. Now STP, we've talked about this before. That was something we learned in the first section. That's a set of conditions. So here's the slide from the first section, and there are the STP conditions. So we know that that's our temperature and that's our pressure as we proceed. This question is not about SATP, so we won't worry about these two in this question. So our pressure, if our pressure is at STP, is 101.3, our temperature is 273.5. We're trying to find our pressure, P2, and we're going to have to convert that temperature because I gave it in Celsius. So make sure you convert that to kelvins. And it's just a matter of writing out your gas law, plugging in your values. Be careful when you cross multiply. So it looks like 100 times 423, and then divide by the 273. And you can check your answer, 156.93. Now again, what are the units on this? Well, back to our pressure of P1, this was in kilopascals. So that means our answer here, that's an A, should be in kilopascals. And there you go. Our temperature went up and our pressure went up too. So there are your three gas laws. So again, be aware of working with the same units when you've got pressure. And don't forget about STP and SATP and converting to kelvins. So go forth and do the homework.
Section 3, the kinetic molecular theory of gases, has 5 postulates. By all means, you can pause the video right now and go over these and write them down. But I will add that if a gas obeys these 5 postulates, which it does 99.99999% of the time, we're going to call it an ideal gas. So we're also interested in scenarios where a gas won't obey those 5 postulates, and these are called a real gas. So real gases deviate from the behavior of ideal gases. They're going to occur at 2 places, very high pressure and very low temperatures. And I do have the rationale here on the slide as well. Real gases will experience forces of attraction under high pressure, so this violates postulate 4 of our molecular theory. So that one. And they will also become a significant portion of the total volume at low temperatures. So that's going to violate that one. So those are 2 scenarios where real gases occur. Well, do we have an application of this? We do. It's called Graham's law of effusion or diffusion. So postulate 5 talks about all gases having the same energy at a particular temperature. And if all gases are created not equally, how is that possible? Well, it comes down to this. The heavier a gas by its molar mass, the slower it's going to move, or effuse or diffuse. And then the lighter a gas, the faster it will move. So again, or effuse or diffuse. So I like to say it's like a skinny man and a fat man running a race. The skinny man's probably going to be most times faster than the heavier person. In this video, we are going to look at the combined gas law. Now consider we've already looked at Boyle's law. We investigated Charles's law, and we also looked at Gay-Lussac's law. Now if we just do a visual inspection here, you'll notice that the pressure term appears up top twice, the volume term appears up top twice, and the temperature terms are on the bottom twice. So we can actually roll this all together into one giant law that we like to call the combined gas law. The way these questions work is you'll be given 5 of the variables and asked to solve for the 6th one. So here's a typical question. We have a 1 liter cylinder filled at 0.08 atmospheres at 20 degrees Celsius and is heated to 35 degrees Celsius, and the pressure has changed to 0.1 atmospheres. What is the new volume? So my first recommendation is you sort through the values in the question. Note that these 3 are together, and we are using atmospheres for pressure, which is fine. Both of our terms are in atmospheres, so we can proceed. If one were in atmospheres and one were kilopascals, we'd have to change one of them. We just need to be consistent. So down here we've got 0.8 atmospheres, we have a volume of 1, and our temperature is 20 degrees, but of course we want to work in kelvins, so that becomes 293.15 kelvins. Over to our second, our pressure here, we again have 0.1 atmospheres. We're trying to solve for our V2, and we'll take the 35 degrees and add it to 273.15, and that gives us 308.15. So these are the values we're going to proceed with to our equation. So cleaning this up, there's our equation. We're going to take all those assigned values and substitute them in, just like that. And there's the exact same equation as well. Now, we're going to have to simplify this. So the way it's going to work is we're going to multiply the tops against the bottoms. So we're going to take those terms together, and we're going to multiply them by those terms. So there are all the ones we circled with the box, and there are all the terms we put as a circle. And all we're going to need to do is, essentially, we're going to divide both sides by this stuff here. So also divide on this side, and you can grab your calculator and start typing it in. And if you've done this properly, you should get an answer of 8.41. Now, what are the units on this volume? So back up at the top here, we had 1 liter. So liters is what we were using. So liters is going to be the unit for V2. So let's tackle another one here with a few more wrinkles in it. We've got a 450 ml cylinder of gas filled at 0.8 atmospheres and 20 degrees Celsius. What is the new volume at SATP? So again, we'll take our variables here. These 3 terms are going to go together. So we have a pressure of 0.8. We have a volume of 450 mils. Now you can convert this to liters, that's fine. Or you can realize that in the second part, we're calculating our volume, so all that means is that our answer is going to come out in terms of milliliters, which is absolutely fine. Our temperature is 20. We'll add our 273 to that, 0.15, so there's our Kelvin temperature. Now, let's not forget the conditions with SATP. We have a pressure of 100 kilopascals, and we have a temperature of 298.15. Now, we do have a problem here, though, is that this value is in atmospheres, and this was in kilopascals, which isn't going to work for us. So we're going to need to convert here. So we're going to go ahead here, and let's convert this value here. So I'm going to have to do it right up here at the top here. So we've got 0.8 times, let's put 1 atmosphere on the bottom and 101.3 kilopascals up top. And that's going to work out to, I think, a little more than 84. So we're going to have 84 kilopascals here. So these are going to be the terms that we're going to proceed with now. So there's our gas law. There is our terms that we're putting in. Again, we're going to do some cross multiplying here. We're going to take the top and multiply by the bottom. Those will go together. And then that top and that bottom will go together as well. So there's all the terms written there. So to solve this one, it looks like we're going to divide both sides by 100 and 298.15. Cancel, cancel. So that also gets divided by 100 and 293.15. And if you type all this into your calculator, you end up with 370.1. And again, the units is going to be milliliters here. And if you get that value, then you have done it properly.
Alright, let's take a look at section 5 here. The molar volume of a gas. So in our lesson we learned that 1 liter of a gas, 1 mole of a gas at STP is always 22.4 liters. So that becomes our molar volume of that gas at those conditions. And if you change the conditions, you get a different size. And so that here should actually say 24.8. Alright, so at SATP it's 24.8. So we can now use those numbers and calculate some densities of gases at these conditions. So, for instance, what if we were trying to find the density of argon gas at STP? Well, we've got our density formula here, which is our molar mass over our molar volume. We can look up the molar mass, and since it's STP, we know that this should be 22.4. So our molar mass is 3995, our density 22.4. And when you divide those out, you should get 1.78. Now the moles back here canceled out, and so that's why our units are grams per liter. Well, what happens if we use the same gas but change the conditions? So this time we're going to look at SATP. So we still have our 39.95, but now we've got 24.8 here. And we divide those out, we get a little bit less, 1.613 grams per liter. Well, what happens if our question's at neither of those conditions, like this one here? So it says, what's the density of 10 grams of argon gas in a 20-liter container? Well, we want to do our density, and we do know our molar mass, but we do not know the molar volume. So we have to dig a little bit deeper here and realize that our molar volume is actually made up of the volume of our gas in liters divided by our moles, which is moles. So in this question, we've got 20 liters. We have 10 grams, which isn't quite moles, but we can change that into moles. So we want to find our 10 grams on the bottom, and our 10 grams times 1 mole, divide by 3995, and we get about 0.25. Might be a little bit larger on your calculator. But now that we have that, now we've got everything we need to go ahead and calculate our molar volume. So remember that this question is saying that our volume was 20 liters, it's in the question, and we just found our moles at 0.25. When you divide those two out, you get 80 liters per mole. Now we can find our density, because we still know our molar mass, 3995, and now we know our molar volume of 80. And when you do that, you get 0.5 grams per liter. The universal gas constant. Let's simplify this a little bit more here. So that's as far as we got. Now what we want to do is we want to get rid of this n. This n's no good on this side here. So let's divide both sides by n, and we'll simplify our gas law here. Now
The only reason we've done this is so that we can actually investigate the units that go with this 8.3145. Now, this is equal to everything on this side, so if we just simply look at the units of the P, V, T, and N that are present here, we should know the units of this 8.3145. So, the units of P at STP, we used kilopascals. Now, that's important because there's a few different pressure terms out there. So this means that anytime you're doing a question using the ideal gas law, you want to be working in kilopascals. Now, when we derived earlier, we used 22.4 liters, so our volume is in liters. On the bottom here, our temperature is always in kelvins, you need to convert. And lastly, we have moles. So all this stuff right here, these 4 units, these are the units of the gas constant. We're not going to need to carry these units along. As long as we know they're there, it's going to help us solve problems. So once again, I want to simplify this gas law here. So all this stuff that we've written on the right side of this arrow right now, we're going to use the letter R to represent it. And there it is. Now we're going to simplify our gas law a little bit. And all we're going to do is we're going to take this T and N here and we're going to multiply it up to the right hand side. So really our final gas law is going to look like this. Pressure times volume will be equal to the number of moles times our gas constant times temperature. This is the ideal gas law. So anytime you see a question involving moles, you want to use the ideal gas law. Don't forget, we always know what R is. It's 8.3145. So let's go ahead and take a look at a problem, and let's apply the ideal gas law to it. So example, what volume will 15 grams? Now, as soon as you see something in grams in the gas section, you can find the moles, which means you're using the ideal gas law. So let's read on here. We've got something at 300 kelvins, so that's going to be our temperature. We have a pressure of 1 atmosphere. Now that causes a little problem right off the bat that we're going to deal with. So once you realize that you do need the ideal gas law, which is that. Okay, so let's start off with our pressure. Pressure is equal to, now we've got it as 1 atmospheres here, but you got to remember back when we derived the gas law, we used kilopascals. So really what we're going to have to do is convert this 1 atmospheres to kilopascals. And I just picked an easy one here because 1 atmosphere is equal to 101.3 kilopascals. So there's really no conversion as long as you understand that it's basically the straight up conversion there. So that is our pressure, 101.3 kilopascals. If this weren't 1 atmosphere, if it were 2.5, then you'd multiply 101.3 times 2.5 to get the pressure you need to continue with here. But anyway, that one should be straightforward, I hope. The next thing is our volume. That's what our question's asking us to find. Next is N. Now, do we actually have a value that gives us N in this question? We have this 10 grams, but that's grams. That's not moles. So we don't actually know our moles, but we should be intelligent enough by now to go ahead and find the moles of argon, setting it equal to those 10 grams of argon times, on the bottom we're going to have our 40 grams of argon. That's about the molar mass. Those cancel out, and that's 1 mole. So 10 times 1 divided by 40 should give us 0.25. So that 0.25 is actually how many moles we've got for this question. So finishing off here, R, don't forget it's always 8.3145, and it has that crazy unit, but I'm not going to write it. And lastly, T for temperature, it's 300 kelvins. It's not in Celsius. If it were in Celsius, I would convert to kelvins, but it's already in kelvins, so let's just proceed. So let's write our ideal gas law. Now we're going to solve for volume, so we'll divide both sides by P. There you go. And now it's just a matter of plugging in the numbers that we have written down. 0.25, 8.3145, 300, and divide that by 101.3. So if you grab your calculators here and type it all in, you should get 6.155, blah, blah. I rounded it here a little bit. Now I guess the question is, what would the units of this volume be? Well, let's not forget here that our gas constant was derived using liters. So that means our answer is in liters. So other questions are out there that are going to say ask for pressure. And you got to remember that if you're solving a question for pressure, this gas constant was derived using kilopascals, meaning your answer will come out as kilopascals. If you do one for temperature, it should come out in kelvins, and kind of so on there. So there, that's one example of the ideal gas law. Again, remember, if you see something with grams in this unit, you're finding the moles, you're probably using the ideal gas law. In this video, we're going to look at a mole map question. So we've got ammonia gas breaking down into a nitrogen gas and hydrogen gas. And here's a problem we're going to tackle. So we're going to determine the temperature at which 1.2 liters of hydrogen gas is produced at 150 kilopascals from 800 mils of 0.25 molar NH3. I probably didn't need to read that, but I did. So what we need to decide right off the bat is what are the states here, what's our path on the mole map going to be. So they're actually, maybe the trickiest part of this question is we've got two volumes. We've got a volume here and we've got a volume here. But what we need to realize is that these two numbers go together, and then all the rest of the numbers in the question go together as well. So we actually have a volume of a something with a concentration. So we're talking about a liquid here. The rest of this information is talking about a gas, kilopascals, temperature. That's all about a gas. So if we look to our mole map, we start with the liquid, or sorry, we'll start with the gas here. Are we given the volume of a gas at a pressure and a temperature? We're not given the temperature, so we can't start as a gas in our mole map. By default, that means we're starting as a liquid, just to double check. We are given a volume, we are given a concentration. So this is going to be our first step on our mole map. So what we're doing here is we're going to be going from a liquid to a gas, and keep it in mind so you can follow the path here. This is going to be our path. And our liquid in this question is the NH3, and the gas in this question is hydrogen. So nothing to do with nitrogen. So let's proceed here. So step one of this question is going to be find the moles of NH3. So we have our formula right on the mole map right here of N equals C times V. And if you look to the question, we are given the concentration as 0.25 and the volume is 0.8. So what I did was I changed 800 mils to 0.8 liters. I need to work in liters in this question here. Multiply those together, we got 0.2 moles of NH3. So we proceeded from our first step. We're currently at the moles of substance A. Next step is the mole ratio. So we want to find the moles of the other substance here, which is H2. So we'll write down the one number we know, which is 0.2 moles of NH3. And we'll come up with our mole ratio. So we've got a 2, we've got a 3 to put in. We want units to cancel, so we'll put the 3 moles of H2 up top, so that is remaining. And we'll be able to cancel out the moles of NH3 on the bottom. And some quick multiplication here should give us 0.3 moles of H2. On to our final step here. So we've proceeded. We have gone from here to here to here. We're at the moles of substance B. And remember, this is about a gas, so we're given in this direction. Unfortunately, the mole map gives us the version of the gas formula rearranged for volume. What we're going to do, though, is we're going to rearrange it for temperature. So all I need to do is divide both sides by NR here. And when I do that, I'll get my temperature is equal to PV divided by the NR. So from here, I'm just going to fill in the numbers. Again, that 0.3 moles is the number we had in the last part in step 2. And we should find our temperature to be 72.16 kelvins, which is ridiculously cold. Doesn't make a lot of sense, but for this problem, that would be the temperature.
In this video, we are going to take a look at a mole map question. Now, the first step of every mole map question is to find the moles of something. So you have to look at your problem and decide, and actually start at the top here and ask yourselves, do I have enough information to find a moles of a gas, maybe a solid, maybe a liquid? So let's look what we've got. We've got a whole set of number right here. And we've got a volume, we've got a temperature, and we've got a pressure. And the fact that we've got a temperature and a pressure tell me that we're probably dealing with a gas here, but let's confirm. We're given a volume, and we're given temperature and pressure. So given all that stuff, we can actually start our mole map right here, and it actually tells us our first step. So step 1 says N equals PV over RT. So we know from our information here that we have a pressure of 95. We have a volume of 1.2, our gas constant 8.3145, and our temperature is given at 300 kelvins. Plug those numbers into the calculator, we should get about 0.0457, and that should be moles of, what substance are we dealing with here? Chlorine gas. So that is our first step, chlorine gas. Alright, so we started here, and step 1 allowed us to get the moles of substance A. Now, if I keep following the map, it tells us we're going to do a mole ratio here. So step 2 is mole ratio. It's always a mole ratio. Now, what are we trying to find? We're trying to find the moles of the other substance, which happens to be aluminum. So let's get the moles of aluminum. Knowing we have that number from our calculator, and that was moles of Cl2. So we need a mole ratio. We've got a 3 in front of the chlorine. We'll put that on the bottom. 3 moles of Cl2. So our moles can cancel. This is about aluminum. There's a 2 in front of aluminum. We've got 2 moles of aluminum. So to the calculator, we're going to multiply this number by 2 and then divide by 3. And if you do that properly, you should get about that many moles of aluminum. Alright, so step 1 is done. Step 2 is a mole ratio, which led us to the moles of substance B, and that is that number on our calculator right now. Now, this question is telling us to do grams. Grams is a solid, so we are going to go in the solid direction here. So our formula here that we're going to be using right in the box tells us that to get our mass, all we need to do is take our moles and multiply by our molar mass. So we are after the grams of aluminum, knowing we have 0. That many moles of aluminum, and all we need to do is multiply that by our molar mass, which is 26.98 grams of aluminum, and that's per 1 mole of aluminum. And if you multiply those two values together, you get about 0.822 grams of aluminum. So to review, this question started as a gas and went to a solid.
In this video, we're going to look at Dalton's law of partial pressures. So we're talking about partial pressure. We're talking about the pressure exerted by a single gas when it's in a system of gases. So Dalton's law of partial pressures depends on the total number of gases, not necessarily the type of gas that is present. And when you've got a mixture of gases, the total pressure is going to be equal to the individual pressures of the gases added up. So the P total is the total pressure. A, B, and C are letters just representing gases in a system. So if we want to do this mathematically, though, we've got a few constants that cancel out, and in the end we're left with this expression here, where the A is representing whatever gas we're talking about. So PA is the pressure of gas A, and P total, pressure total, is usually given in the question. And this last part here is our mole fraction. So what we're going to need to do is find the moles of gas A and also find the total moles in our system. So we've got a typical question here. We've got 10 grams of argon, 16 grams of oxygen, and 22 grams of carbon dioxide. And we're actually given our total pressure rate here is 100 kilopascals. We're going to want to find the partial pressures. So our first step is we're going to find the moles of each gas. So let's find the moles of argon. So if we have 10 grams of argon, argon's molar mass is 39, so basically 40. You can cancel out the units, and you're left with about 0.25 moles of argon. Moles of oxygen is going to be 16 grams, and its molar mass is going to be 32. So again, we can cancel out the grams, and that gives us about 0.5 moles of oxygen. And lastly, for carbon dioxide, we have 22 grams, and we again end up with 0.5 moles of carbon dioxide here. So our next step is we're going to add up all the moles. So our total moles is going to be equal to that 0.25 moles of argon plus the 0.5 moles of oxygen and the 0.5 moles of carbon dioxide, giving us a total of 1.25 moles. Okay, our next step is we're going to use that equation from earlier in the video to figure out the pressure of each gas. There it is. So gas A in this case is going to be argon. Now I do want to point out that our pressure total was given in the question as 100 kilopascals. So that's supposed to be 100 kilopascals there. So we've got argon. Now recall that we found there are 0.25 moles of argon, and remember this bottom number is our total moles discovered. So when you go 0.25 divided by 1.25, it equals about 0.2, and then 0.2 times 100 gives you 20 kilopascals. I do want to point out here, if your gas term is not in kilopascals, say it's in atmospheres, that just means your final answers will be in atmospheres here. So it doesn't matter. You can work in any pressure term that is given. So our second gas was oxygen gas. So the only value that's going to change is our moles of oxygen. This time it's 0.5. If you divide 0.5 by 1.25, you get 0.4. 0.4 times 100 gives us 40 kilopascals. We can do a bit of a shortcut to find the pressure of our last gas using this equation here.
We know that our total pressure is given as 100. We know that we found our partial pressure was 20 of the first gas, 40 of the next one. So some rearranging and basic math should give us the partial pressure of carbon dioxide to be 40 kilopascals. Notice that our three pressures, 20, 40, and 40, all add up to our total of 100 kilopascals. If you enjoyed this video, feel free to subscribe to my channel. Thank you very much.